In the previous section, we tried to construct a new solution to an ODE based on the fact that we knew the first solution of that same ODE. So here we're going to look at this in a more general way. This tool is called reduction of order. So let's look at it. We have y second. In this case, we don't even restrain ourselves to constant coefficients, so the coefficient of y prime is p of time, plus qt equal to 0. And we know we're given a first solution, y1. We wonder, can we construct y2 based on the knowledge of y1? Can we do it in a general way? Or is second order linear homogeneous ODEs with repeated roots the only case in which this works? It turns out that it does work in a more general approach. If we plug in y second equals v times y1, y2 equals v times y1, we can compute the derivatives of y2 based on the derivatives of v and the derivatives of y1. So y2 prime is v prime y1 plus v y1 prime. And y2 second is v second y1 plus 2 v prime y1 prime plus v y1 second. And we need y2 to satisfy our initial ODE. So we need the second derivative of y2 plus p, possibly depending on time, first derivative of y2 plus qt y2 equal to 0. Just notice that y is the linear term y is missing on the first version of this function. It's a typo, I'm sorry. Anyway, we want to solve this ODE in y2, and we write y2 prime and y2 second and y2 itself as functions of v and y1. So we write down everything in the most extensive form. We have v second y1 plus 2 v prime y1 prime plus v y1 second plus pt multiplied by v prime y1 plus v y1 prime plus qt v by y1 is equal to 0. If we turn things around in a similar way as we did before, so we put together the derivatives of v, we have v second y1, v prime, something that depends on y1 and y1 prime, and v, something that depends on y1, y1 prime, and y1 second. But let's look a little bit more at the coefficient of v. That is exactly the ODE y1 solves. So the coefficient of v is just equal to 0 all the time. That means that we can drop that coefficient and we get to an easier ODE that is v second y1 plus v prime, something that depends on y1 and p. This might look like a second order ODE, and in a certain sense it is, but if you replace v prime by a new function, u, this turns out to be a first order ODE, a first order linear ODE in u that we know how to solve. So if we solve for u and then we integrate in order to retrieve v, we can write y2 as v times y1, and we only have to solve a first order linear ODE instead of a second order linear ODE. So we have decreased the order of the ODE we need to solve. Just by knowing one solution and trying to build a second solution based on that. We have no information about what sort of solution we need in order for this to fit. It works for all types of solutions. Let's look at an example of this. We are looking at 2t second y second plus 3t y prime equal to 0 for t bigger than 0. Now this is a different format than the one we looked previously, but it would be enough to just divide everything by 2t second to retrieve what we had before. So let's see if it works also in this slightly stretched example. We're restricting ourselves to t strictly positive, so we can divide by 2t squared without a problem. We are given that the first solution, y1, is equal to 1 over t. Let's try to find the fundamental sets of solutions. So a second solution that can complement y1 in a fundamental set. We assume it can be written as vt times y1. And as before, we plug in y2 in the ODE, and we write the derivatives of y2 as derivatives of v times y1. So we have 2t second block of v second y1 plus 2v prime y1 prime plus v y1 second. And then we have 3t v prime y1 plus v y1 prime. All of this is equal to 0. We mix things around in such a way as to have v prime times something, v second times something, and v times something else. And we notice that the coefficient in front of v is exactly the ODE we started with y1. So that simplifies to 0. So now we have an ODE that depends only on v second and v prime, and with y1 appearing everywhere. So we have v second multiplied by 2t squared y1 plus v prime multiplied by 4t squared y1 prime plus 3t y1. All of this equal to 0. We remember ourselves that we started knowing that y1 is 1 over t, and y1 prime, therefore, is minus 1 over t squared. So we plug this information into the ODE that we're given, and some things simplify out. So now we have v second multiplied by 2t plus v prime multiplied by minus 4 plus 3. This simplifies to 2t v second minus v prime equal to 0. This is a second order ODE in v, but it's something that doesn't depend on v directly. It only depends on the derivatives of v. So we introduce a new variable, a new function that we call w, that is the first derivative of v. Then the equation for v becomes an equation for w, in which we have 2t w prime minus w equal to 0. Then we can solve at whatever method you want. I like separable equations, so I'm going to write it as v prime divided w prime divided by w equals 1 over 2t. That means that it's dw divided w equals 1 over 2t dt. We integrate both sides. We get a logarithm of w on one side and 1/2 a logarithm of time plus c. So whatever method you want to choose to solve 2tw prime minus w equal to 0, you should get to w equal constant times square root of time. And this is the first derivative of v. So we have to integrate it once in order to retrieve v itself. So we integrate this, and it's c times t at the power 3/2 plus k. So v is the result of a second order ODE. So it is natural for it to depend on two constants that we can choose. But we take this result for v and we plug it in the information we know about y2. y2 is, by construction, v times y1. So it's c1 t at the power 3/2 plus c2, that is v, multiplied by t at the power minus 1. We can simplify things around, and it is c1 square root of t plus c2 t at the minus 1. Now, t at the minus 1 is already y1. So if you're trying to construct a fundamental set of solutions, so you want to find the simplest format in which that works. So we can, for y2, we can drop the term that is exactly y1, because it's an additive term. So we have something, something, something plus y1. If that's the case, you can drop y1 and may have a simpler fundamental set of solutions. So with this, our fundamental set of solutions is t at the minus 1 and square root of t. We can check to test that this actually works, and we want to compute the Wronskian of t at the minus 1 square root of t. In the first line of the matrix, we write t at the minus 1 is square root of t. And on the second line, we write the first derivatives. So minus t at the minus 2 and 1/2 t at the minus 1/2. And we compute the determinant of this matrix. And through the steps, we compute that to be 3/2 multiplied by t at the minus 3/2. T is strictly positive. So this is not a problem to compute, and it's different than 0 for every t, by the way. So our Wronskian is different than 0, so the solutions that we found are indeed a fundamental set.